Hi, my name is Stephen Wang. Thank you very much for joining me. This is my assignment, The Little Elephant and the Magic Square. It's problem code forces 259B with difficulty 1100. The assignment is workshop number 1 for CSC 575 algorithm and complexity analysis for fall 2021. So let's get started with the outline. First, for the assignment, I'm going to describe the problem and define the input parameters and solution goal. Then I'm going to provide several examples of the correct input and output we'd like to see. Then I'm going to show and explain my code and algorithm in correctly solving this problem. Afterwards, we'll analyze the asymptotic bounds on the time complexity of the algorithm. And finally, we're going to analyze correctiveness and confirm using proof. So let's get started with what's the problem? What are we looking for? What are we going to try and do today? And we're going to try and help Little Elephant. So Little Elephant loves magic squares very much. A magic square is a 3x3 table. Each cell contains some positive integer. At that, the sums of the integers in all the rows, so 1, 2, 3, the columns 1, 2, 3, and the diagonals 1, 2 are equal. This means we have 8 checks, right? This is an example of a magic square, and if you want to take the time, the sum of all of the rows, columns, and diagonals are 15. So Little Elephant remembers one special magic square, and he started to write this square on a piece of paper, but as he wrote, he forgot all 3 elements of the main diagonal of the magic square. Now, fortunately, Little Elephant clearly remembered all the elements of the magic square did not exceed 10 to the power 5. So there are no values in any of the cells that are over 10 to the power 5. So we need to help Little Elephant and restore to him his original magic square, given the remaining notes that he's provided. So the input is Little Elephant's notes, or the supposed cell data that we have, right? You'll have 3 lines of input containing Little Elephant's notes. The first is the first row, the second line is the second row, and the third line is the third row. And the main diagonal elements that have been forgotten are represented by zeros. Now, they do specify and guarantee that the nodes contain exactly 3 zeros and they're all located in the main diagonal. And it's also guaranteed that all the positive numbers in the table that they provide do not exceed 10 to the power 5. Now the output should be a square as well, 3 lines, and each line print 3 integers, and it should be Little Elephant's magic square. Now there may be multiple solutions, and we're allowed to print any of them. We just need to find one. Now note that the 3 variables, the 3 integers that we need to print must be positive and not exceed 10 to the power 5. And they do guarantee a solution. So I have a brief recap here, just so you can take a moment. We need to find the magic squares. Magic squares are 3 times 3 tables, each cell containing a positive integer, and the sum of the integers in all the rows, columns, diagonals must be equal. Now, Little Elephant remembers all the elements within the magic square except those along the main diagonal. They define this as top left to bottom right. And we need to restore the magic square based on Little Elephant's notes, but no cell can exceed 10 to the power 5. We only need to worry about printing out correctly the values they provide to us, because they already guaranteed none of the values that they provide are over 10 to the power 5. Now, the input needs to be 3 lines of input representing the 3 rows of the magic square. The missing elements are 0, and we need to provide 3 lines, and it needs to look like a square, right? And so these are examples of the input. And as you can see here, right, all ones turns into all ones, because then the sum is 3. And these, they do sum up to 15, just like the previous example. And these are some other examples that I found online that I like to use to test my program, right? So let's get into it. I'm going to show you the program that I developed, and you know, it's a pretty cool thing, but the only programming joke I know is my own code. So let's hope it works out well. We have the standard libraries program. This is to initialize the original array / square. This is the input loop for providing the formatting for the input. So obviously, right, first create a loop for the rows, then the columns, and then this will allow input in with spaces for consideration within the magic square. And now the condition check for correct answer, right? I define my variables top left, center, and bottom right. Those are the missing, and we'll get into this algorithm in much more detail later in the presentation. But finally, we got the final assignment of the first result. So once it passes through this condition check, our algorithm, once we have a solution, that's the final assignment, and then the output. So it prints out the result that we have, right? So let's go ahead and test it. And of course, we're going to start with the examples they provide to us. So 0, 1, 1, 1, 0, 1, 1, 1, 0. So that provided to us the correct answer. Fantastic. It was all ones. Now let's move on to the next stage. This one's a little bit more difficult. 0, 3, 6. 5, 0, 5. 4, 7, 0. We also get the correct answer, 636, 555, 474. Now we want to test one outside of the examples they provided to us just to make sure it's not cherry picking and targeting just the examples, right? So I'm just going to pick a random one out of these. Let's go ahead and pick, let's say the last one, 092, 307, 810. Okay, so the result, 492, 357, 816. All right, we can assume that for now, at least, the algorithm is working for correct input and output. And these are examples of how it should look coming out, right? So let's get into the code, right? This is the algorithm just flattened out so that it's a little easier to read, bigger font. So the for loop is a for loop to check all positive integers from 1 to 10 to the power 5 within the top left cell. So we'll define this variable first. Remember that the solution really is just finding 3 variables that the combination creates the magic square. So I brute force this by making a for loop that goes from 1 to 10 to the power 5. With that one variable, then we can define the sum. And the sum is, we define the sum here as the entire row, right? We add together these three cells. Once we have the sum, that sum is supposed to be the magic number, right? It's supposed to be the same for all diagonals, all rows, and all columns. So therefore, I can start defining the center and bottom right. But with each definition, if I divide in the center, if I define bottom right, I'm checking to make sure it follows our parameters. Remember, the parameters are each value needs to be over 0. It needs to be a positive integer, so over 0, and it needs to be under 10 to the power 5. So in either case of these, we have a continue statement. So it forces it into the next iterative loop in order to not have to go through the entire for loop. And these are further validity checks, but rather than checking to make sure that the cells are valid, because remember, it's just those 3 cells that we need to check, they provide to us a guarantee that the other cells have positive integers that are between 0 and 10 to the power 0 and 10 to the power 5. On only 3 zeros, so it's 1 to 10 to the power 5. In this check, it's to check to make sure that the first one is the diagonal. If that follows the sum, then we have the columns, and then we have the other diagonal, right? And my general thought process doing this was to use a brute force check using one variable to check any possible matches. So I would first define the missing variables and then check validity conditions and only break out of this for loop with a valid answer. So it's just checking every single possible first variable and seeing if the resulting the other remaining 2 can follow along in a sense with the data that we've been given. When I analyzed the asymptotic bound on this algorithm, it turned out to be theta 1. And this is because my algorithm really is just a for loop with a 10,000 iteration of several simple statements, right? If we look through it, I got one constant time loop that may or may not get up to 100,000, and I will get into that, right? It's 100,000. Because it's 10 to the power 5. Yeah, 100,000. We have a constant time loop. That's going to be anything below 100,000, 1 to 100,000. Then we got statements. These are theta 1 because they're very simple arithmetic statements or checks, right? And the rest of the code really are just validity statements that lead into continues that break the cycle early. So you're not guaranteed to have to go through the 100,000 or 10 to the power 5 loop every single time. Technically, the complexity is 100,000 minus 100,000 minus whatever number comes up as the first variable. So if the first number for some reason is 60, then you'll only have to go through 60 loops before they find a result. It's really just to be comprehensive in case you have an extremely difficult or complex magic number for some reason. But that's why I believe the asymptotic bound on the time complexity of the algorithm is theta 1. Now, analyzing the correctness using proof, my solution doesn't really require a loop, or it isn't a recursive loop that depends on itself, so to speak, with variables. It's a brute force finite sequence of arithmetic statements and Boolean validities. So instead, we're going to prove using proof by contradiction. For review, proof by contradiction is that we assume the statement to be proven false and work to show its falsity until the result of that assumption is a contradiction. So I'm going to pretend, or I'm going to work towards the assumption that my algorithm doesn't work, but then prove that it does, as long as it fulfills all the requirements. If it fulfills all the requirements, then by contradiction, it can't fail. So what are the requirements? So first, obviously, it needs to fill the requirements of a magic square. Magic squares have the same sum amongst its rows, columns, diagonals. Other ways we could fail is if there are values that aren't positive integers, and if there are values larger than 10 to the power 5. Now, what does my algorithm really say if we break it down, right? So first, value A, or the first top left variable, is going to be between 1 and 10 to the power 5. Next, the first row is going to define the sum, or sum x. Then we define the center variable e from x and the other cells within that row. And then we do a validity check to see if e is less than 0 or negative, or if e breaks the 100,000 barrier. On the other hand, right, when we have the, and then this is the final variable, right? Like this is going to be the bottom right, same validity check. Let me just double check here, because now I have corrected myself so many times. This should work now that I added the extra 0, and it does. It's just very rarely do you get numbers that big from the examples given. But yeah, x equals a to a plus e plus I, that's the diagonal. B plus e plus h, that's a column. C plus e plus g, that's a diagonal. C plus f plus I, that's another column, right? So what does that answer? There are values that aren't positive integers. Well, we already have the validity checks, right? We have the validity checks here for if e is less than 0, and this should say and greater than 100,000. If I is less than or equal to 0 or greater than 100,000. And so each one of the independent variables that we defined do have these validity checks that make sure that it goes on to the next loop if they fail, right? So they are all, none of the values are larger than 10 to the power 5, and they're all positive integers. So both of these fail. We do not get to fail that way. Now, the other way we can fail is magic squares must have the same sum amongst its rows, columns, and diagonals. I labeled here each line and what they cover, right? So line 1 covers row 1, line 2 covers row 2, 3. Then we have this diagonal 4, 5, 6, 7. They need to pass each one of these and make sure it fulfills that requirement in order to move on. Now, if you notice, I did leave one column, and this is to proof by contradiction, saying that if we have all of these other assumed as true as my premise, then we can conclude this as well, and therefore you cannot say it won't be a magic square. So a plus d plus g, we're trying to make it fail. It cannot equal x, right? Well, a, as we know, is x minus b minus c. D is x minus e minus f. And g is x minus h minus I. But that still can't equal x, right? That's 3x minus b minus c minus e minus f minus h minus I. And that still can't equal x. Sure. And then we have 2x because we move the x over here. We move every other variable equals b plus c plus e plus f plus h plus I. Okay, sure. We could say that it doesn't equal 2x, except when I rearrange this into BEH, CFI, these are two different versions of x. 2x has to equal 2x. So Ergo, as long as these premises remain true, then the final premises where A, D, and G equals X as well has to be true as well. And then we have our proof by contradiction. There's no way we can say it won't be a magic square if these are the requirements and definition of a magic square. So this has been my presentation. I hope you guys had a great time. Thank you very much. I had a fun time playing with the little elephant, and I hope you have a great day, okay? Let me know if you have any questions or concerns, and I'll be posting this up shortly.